Alright, hi everyone, welcome to my YouTube channel, City of Electrons. And in this video, we are going to deal with something we talked about from the previous video. So in the previous one, we said a system, of course, system processes or operates on signals. So systems can be represented as differential equations, as Laplace, convolution integral, block diagram, and then state space representation. Okay, so what we want to do in this particular video is the first representation, which is differential equation. That is, we want to represent a system using differential equation. Note that a system processes or operates on signals. So recall that a signal, like I just wrote down here, since a signal is a function of time, we have x of t. That means x is a function of t. Okay, so that means x of t is a signal. Now let y be output signal and x be let y be output signal and x input signal. Yeah, so y of t output, x of t input. Now a system which processes signals can be expressed or represented with differential equation. Okay, so what we are actually doing here is this is what we are doing here. We are saying now we are dealing with just the output. Okay, so if you see y of t, y of t, y of t, that's what you see here. We are just talking about the output for now. Well, we are clear with how to represent the output using differential equation. We'll now talk about the inputs. It's the same. Okay, so just look at it now. So now we are saying that this is the signal y of t. Okay, now to represent it in differential equation, we are just saying take the first derivative of y of t. Okay, so if you take the first derivative, differentiating y of t is simply dy of t over dt, or if you want to say dy dt, that's okay. All right, now take the second derivative. Observe, we are just dealing with this guy. Okay, y of t. Differentiate it for the first time, you get dy of t over dt. Differentiate it the second time, you get this d squared y over dt squared. Okay, a1, a2, a0, they are just coefficients, they are just constants. Okay, it doesn't really like they are just constants. Okay, so we can decide to put q1, q2, whatever, they are just constants. Now the main thing you have to bear in mind is that this signal is being differentiated. This is the signal, this is the first derivative, this is the second derivative. We can go on and on, third derivative, fourth, fifth, sixth. Okay, we can go on and on until the point where we have the n minus 1, until you get to n. Like you can differentiate second derivative, third, fourth, until to the nth derivative. Okay, now before the nth derivative, before n is what? N minus 1 now. Okay, so something behind n should be 1 less than n. So before you get to the nth derivative, that's how we put n minus 1. Okay, so this differentiation is in the nth order. You know, if we have differentiation that has the highest power as 2, that's second order. If the highest power is 1, is first order. But in this example here, the highest order is n, so this is an nth order differential equation. If you look down, I think I wrote something like that here. Yeah, so this is an nth order differential equation. Note that a and b are real coefficients. For now, we are just talking about the output, and I said I'm using only a for the output signal. So a0, a1, all these are just coefficients. Okay, so if you understand what I just said here, of course you can pause and rewind the video, take it backward or whichever way. Now if you understand what I just said here, you have gotten a large portion of this video. Okay, a signal y of t just being differentiated, and you sum up the differentiation. That's just it. But the a1, a2, next a, they are just coefficients. Okay, now this is representing the output signal in differential equation. As straightforward as that, guys. Now, this what I've written here, we can also write it in this form, or that's writing it in this form. Of course, this is the first term. This is what we have here. The next term, that's the first derivative. You just put a dot on top of it. So this, everything. Oh, in that one. Everything here is the same as everything here. Okay. Same to this. This squared y of t over the t squared is the same as y dot dot. So you put your t. Dot dot meaning second derivative. So I think this expression is even easier. Like it's shorter, it saves your ink, you know. So of course, same thing. We can increase from the dot 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 until we get to the nth dot. Nth number of dots. Of course, the one before the nth number of dots is n minus 1. Okay, so I guess that's clear enough. And of course, this guy just follows a0 a just follow from a0, a1, a2, a3 onto an. Okay, now this expression here, I decided to put it in this third form because this is what we have in our notebook. So everything here is exactly the same with what we have here, just that we reverse this arrangement. We reverse the arrangement. That's just what we did. Meaning this one, we write this one first. Look at it. This term, we wrote this one first. Look at it here. Okay, and then this term, we wrote it next. Look at it here. And then this term, we wrote it here. And then what's next? And this term, we just switch the pattern or arrangement, whichever we want to put it, and this one goes last. Okay, so we just switch the order, so it doesn't really change much. Okay, now, so that's for the output signal. However, just bear in mind that this arrangement we've done for output signal y of t is the same. We can just apply it to the input signal x of t. So for output signal and input signal, these are output signal which we've just done here. So we just wrote exactly the same thing here. Output signal equals input signal. So for our input signal, trying to make it easy for us to see the whole thing. Is this big enough? Yeah, I want to see from start to end. Okay, now look at the first thing here for our output signal is similar to the input, just that where you have y of t, here you have x of t. Y of t for input, y of t for output, x of t for input. An, this time I try to use bm. Okay, so just exactly the same pattern, just that instead of y we use x, and instead of a we use b, and instead of n we use m. The rest things remain the same. Now I said it can be any letter. Okay, these guys can be any letter, but whichever letter you use, just be consistent. Just maintain that letter or true. Okay, so I hope that's clear. So when we say this is an nth order differential equation, we are talking about this equation right here, this complete equation, not just the output, but the output and the input. That's an nth order differential equation. Note that a and b are real coefficients. Okay, a and b are real coefficients. So signals or systems represented in form of differential equations can be solved using Laplace transform. Okay, so of course this will lead to a transfer function, which is the ratio of output signal to input signal. So h of x equals y of s all over x of s. That means these are outputs, no, this way, these are output signal divided by our input signal will give us the transfer function. Okay, so when we talk about transfer function, it's just output over input. So that we'll also talk about in the next in another video, but this video will just see how we represent see the differential form, or how differential equation looks like when we're talking about input and output signal. Okay, so in the next video we are going to talk about an example which will help us work with this differential equation and Laplace transform. Laplace transform because to really solve these differential equations, man, it's just better we take the Laplace transform than use normal arithmetic operations or simple algebra, simplify it and then take the Laplace inverse, then we'll get our output or output signal or whatever we're looking for. So this will be all for this video. Of course, go through the video over and over again once you get what we are really talking about, and then of course see you in the next video. Thanks a lot for watching, and bye for now.